Okay, today I'm going to update you on this little mixing device, chemical mixing device. We'll look at it under the microscope. So chemicals are used for a number of purposes in cryopreservation. The main purpose is to sort of interact with the water molecules and hopefully avoid ice formation. We get these chemicals in, obviously high concentrations. There is a desired concentration, for any experiment you may have of the desired concentration that you want in the tissue. Some tissues can handle just being immersed in that final desired concentration, just directly immersed into it, but other tissue can't. And a reason it might not be able to is different chemicals move across cell membranes at different rates. So if you immerse in a very high concentration of a chemical, water moves very easily across membranes. So the water will leave the cell will dehydrate, and then as the chemicals are moving back in, and we call these chemicals cryoprotectants. So if you hear me say that, that's what I mean. And there's CPA is a short name for it. So the cryoprotectants will move, can move as they're moving across the membrane, then the cell will, sort of slowly expand again. And this rapid contraction expansion can be damaging to the cells and the tissue. So in a lot of experiments, we want to kind of ramp up that concentration. So what you'll have is kind of your final ratio that you want of the non-water chemicals, and those will be in sort of their highest concentration. And then you have water, and you'll be mixing them together throughout the experiments. You're ramping up the cryoprotectants in the tissue. And this is what's typically used to mix those together. So you put this in a tube. It's called a static mixer, and it has these little helices that are rotated by 90 degrees. And so you'll combine the two tubes, and you'll pump them through this static mixer before it goes into the tissue, before the tissue is exposed to it. I'll show a video right now of the end result of an experiment I did with this, and you can kind of see how it's still not well mixed. Like if it was well mixed, you wouldn't be able to see the needle really moving the liquid around. Okay, so then what I decided to do is, and for my experiments, it's even worse. So I might be changing. We're going to have control over each of the chemicals independently. So we may be changing the ratios dynamically. So during that experiment, we'll be changing the chemicals. So we need to mix it during the experiment and have it mixed really well. So I'm starting with, and what we can see here under the microscope is 50% glycerol by volume in water. And I'll just show you with, I'll just move it around a little bit. But you can kind of see the swirliness. That is that it's not well mixed. And now I'll turn on so what this just is a little motor. It has a little, pinion, and then a spur gear. The spur gear has two magnets on the bottom of it. And then there's a little bar or mixing bar with the magnets that's kind of matching the magnets on the spur gear below. And as we turn it on, so here we go, it's starting to spin up. And I'll figure out, the exact best ratio of it, or best RPM for this. So it's spinning, and this likely will just be continually spinning during the experiment. And then as we stop it, and also this is, again, the worst case scenario. Okay, so as we stop it now, as I'm kind of moving the needle around, it just, looks like water, but just happens to be much more viscous. So it's well mixed. So that should work well. So there'll be one of these on each of the little experiments in the array of experiments. And it'll be pumping, through this and then back into the chamber where the actual experiment is happening. But yeah, should work well, I hope. Okay, I'll update you next time. Thanks.